All right, thank you all for coming. My name is Mark Stock. I'm an employee at Hewlett-Packard Enterprise, and speaking with me will be Daniela Pejovich. We're going to talk a little bit today about Exascale, Frontier, some history, and what skills you need and how to get involved. So I already talked about all this, right? I'm going to mention who Hewlett-Packard Enterprise is, kind of a surprise, why we build computers at all, a little bit into the hardware, and then stuff other than hardware, and then, like I said, how to work at Exascale. So Hewlett-Packard Enterprise, here's our CEO, Argentinian. This was a company that was broken off of Hewlett-Packard, so you're familiar with them from the printers, in 2015, focuses on the enterprise computing branches because Hewlett-Packard owns the PC and printer stuff and more consumer stuff. Hewlett-Packard made this laptop, Hewlett-Packard Enterprise makes supercomputers. HPE bought Cray in 2021, and that was a big influx of IP and talent. And that was after Cray had won the contract to build the first two exascale computers in the US, Frontier in Oak Ridge and El Capitan in California. And also Cray and HPE are building the infrastructure for the third exascale computer, which is going to go into Argonne National Lab. And Intel is making the CPUs and GPUs for that one. Relatively big company. So you're going to hear me talk a lot about the two main types of large-scale computing. And the first one is called throughput computing. And this is probably the one that we're most familiar with because this is tasks that are relatively independent, and we don't need to transfer a whole ton of data between these tasks. So examples are pretty easy to come by. These are the first two that came to mind. You don't send a ton of data, you don't receive a ton of data, but you do a little bit of work. And those tasks can be parallelized relatively easy. And cloud computing is the proper solution for this. Also the at-home networks of distributed computing. You'll see a lot of commodity hardware, a lot of very, very large scale machine rooms, but you don't need amount of communication between things because you're not working on the types of problems that we'll get to in a second. So scalable, this is the difference. This is what Exascale is really about. Scalable computing is where you have very large tasks with a lot of parallel things to do, and they're all interdependent. So you have to move a ton of data to move forward a certain time step or whatever. And examples of this are things like physics simulations. So this has traditionally been, I guess you can even say this is why supercomputers were built in the 40s and 50s, is we're trying to figure out how a nuclear bomb went off. So von Neumann and a crew of people kind of invented all the technologies that led to computational physics. But of course, that's not all that we're working on. There are also very large machine learning tasks that are applicable to a very large scale computer like this. And to really make scalable computing work, and of course, physics, you need high performance mathematics, you need very low latency interconnects, and it helps to have the hardware and the data in the same place. So we'll talk a little bit about how Frontier does that. So Exascale as a concept kind of started being talked about in 2008. DARPA created a study that very effective study like this. This is the title page about Exascale, and they made some projections, but they also showed what the current biggest supercomputer was, and this was at Los Alamos National Laboratory. It was the first to break a petaflop per second barrier, which is one with 15 zeros. InfiniBand interconnects. It had a 9-core, 3 GHz CPU, IBM blades, and a Linux operating system. This looks really familiar because this is almost the same architecture that we have for supercomputers today. We have low latency, high bandwidth interconnects. We have blades. This was Linux. Now, back in 2008, Linux was not a widely used operating system for supercomputers, but it quickly overtook all other operating systems, and now I believe every computer on the top 500 list runs Linux. So the challenges that the DARPA study mentioned, that you kind of can't just get to Exascale with business as usual. The challenges were first about energy. It takes a certain amount of picojoules to do one floating point operation. certain amount of energy to store data, certain amount to communicate that data. And that energy was not there yet. Storage, you're of course solving a very, very large problem to get to an exascale level problem. So you need large and fast storage. And of course, you need to have tons of concurrency, many millions of threads operating at the same time, something that was just simply wasn't happening in 2008. And then obviously, when you have this many machines, this many parts, mean time between failures suffers. So there were some projections in a slightly later report for what this computer might look like. This is transistor count. The top row of that is 100 billion transistors on a single silicon die, not silicon chip. And this projection was actually fairly accurate. The MI250X that we use in Frontier has 58 billion transistors, which puts it right there. This is clock speed. You remember the 2008 supercomputer was IBM running at 3.2 gigahertz. We're running slower than that. So that guess of it looks like 100 gigahertz, if you look at 2020, that was wildly wrong. But this tells you a lot about what technology can do in 14 short years and how the physics of how to make these transistors really affects how you make an exascale machine. I think we're going to go to a video next, right? This, hopefully. That was the only PR video that we have. The next video we're going to show in a few slides is, I'll get to that actually. It's not a PR video. So let's take a little look at the hardware. First of all, it's located here. This is Tennessee Oak Ridge National Laboratory. It's a Department of Energy laboratory, and it has housed powerful supercomputers for quite a while. This is a picture of the lab. Summit was the previous largest supercomputer at Oak Ridge National Lab, and it when it was installed in 2018, it was the #1 fastest supercomputer in the world. It held that spot for 2 full years, and now Frontier is going to take that. Frontier has already taken that #1 spot. So this is a little picture of the machine room, and these are a whole bunch of HPE Cray cabinets, and we'll look at where the components are. So Frontier itself is this big chunk here, 74 compute cabinets, and 1/3 that many cooling distribution units. Frontier is water cooled. We'll get into that in just a moment. Next to it, this is the Orion storage system. This is a 700 petabyte storage system connected to Frontier. This is going to be a lab-wide storage system. And this little thing over here is called Crusher. Crusher is a machine that we've done a lot of our development on. Crusher was stood up about 6 months before Frontier. Frontier is fully installed and working. It's in final stages of acceptance right now, but Crusher's been there for almost a year. You might notice if you look at the top 500 list from June, that there's a machine at number 29 called Frontier TPL, I think, and that is the Frontier test system. That is one cabinet of Frontier, and it already made number 29 on the top 500 list. So Crusher is 1.5 times that big. Crusher would be, I think, number 18 if we ran HPL on it and tried to submit it. So these are the cabinets. I don't have a good picture of the compute cabinet open, but we'll see a little bit more of that later. And then on the right, this is not a jet engine. This is the cooling distribution unit. All parts of this machine are water cooled. The CPUs, the GPUs, the network equipment, all water cooled. No air fans in the supercomputer itself. So you need pretty big pumps to move a ton of water. A ton, probably multiple tons. Here's a close-up of the blade. Now, each of these blades holds two separate nodes, and each node has one of these EPYC CPUs, 64 cores, and 4 AMD MI250X GPUs. We're going to dig a little bit deeper into this hardware. So this is one of the nodes. Now, this was created with HWLoc, a little program to look at the hardware and the interconnects between them. You'll notice that we're kind of like biasing what we're looking at to the CPU. Note that the CPU, this big chunk on the left, this is 2%, less than 2% of the computing power of this node. But it has these individually addressable cores and a NUMA architecture, non-uniform memory access. So this is an important thing for HWLoc to show. On the far right, we have the other 98% of the compute power for this node. In 4 GPU packages, each GPU package, though, has 2 graphics compute devices. They're labeled GPU here, but we like calling them GCDs. And if you notice, I don't know if you can read this way on the bottom, on each of these GPU packages, between the 2 GCDs, there is a total of 400 gigabytes of memory bandwidth between those 2 GCDs. And each one has 64 gigabytes of HBM2E memory. There's a lot of memory bandwidth going on here, and there's a lot of compute devices. And then on top, there's this little line over the PCI bus to a non-volatile memory device. This is called burst buffer. There's no hard disks on this machine. If you want to write data, you should probably not write it to your home directory, because that's going to go over the network off to that big Orion file system. You're going to want to write it locally to this fast SSD, or keep it in memory, better yet. Let's zoom in on the MI250X. So this is AMD's top of the line, not workstation, machine room GPU. There's a lot of stuff going on here, and you can probably not read it. On the left is one of the GCDs, and in it are 110 of these compute units, CUs, these little slivers. Connecting to them are a large L2 cache. There are memory accesses to the HBM memory, and then there's this infinity fabric connecting both of those GCDs and also going off chip to other GPUs. And then we'll zoom in once more to this compute unit. So in each compute unit, there are 4 of these 16 wide SIMD kind of vector shader cores. Now, on NVIDIA, if you program for CUDA, you'll notice that you'll probably remember that the warp size, they call it a warp, is 32. So on the AMD chips, there's a thing called the wavefront size, which is the same thing as warp, which is 64. Another piece of advice when you're programming for new architectures is don't fix your warp size to 32. Assume it may change. Each of those wavefronts of 64 threads operates on only one of these 16 wide SIMDs. It just runs 4 operations, 1 per clock. Now you see that there's 4 of those 16 wide SIMDs. You'll obviously want to have 2 wavefronts on each of those at every time. So you're going to want 8 wavefronts. Whereas if you remember programming for CUDA, if you've done that, you want to try to have at least 3 or 4, not wavefronts, the wavefront equivalent in flight at any given time. So there's a lot of layers to this memory hierarchy and this compute hierarchy. This is down to the bottom. What I'm not going to get into during this talk is the matrix cores. Now that's a huge topic, obviously. Machine learning is huge. We expect the next big supercomputers to be mainly machine learning supercomputers. So those matrix core units perform a lot of floating point operations, and they're going to become, in my opinion, a much larger part of any of this silicon in the future. We're still not going to get rid of those vector cores, though. So where do the 18 zeros come from? Exascale is 10 to the 18. On October 18, HPE celebrated Exascale Day, where, an excuse for a party, right? So my mind is blown by these massively big numbers. So I tried to break it down. Where do these 18 zeros come from to give us this kind of floating point performance? So the clock itself I put 1.7, but that's really only if you're running a very short workload and on like one of the GCDs. So thermal obviously is a big issue for these big computers. So I'm just approximating 9 zeros from the clock speed. It's about 1.6, 1.7 gigahertz. We get some more parallelism from each compute unit. Like I said, I had 64 floating point function units. Each of those can do one fuse to multiply add per clock tick. So that's 128 floating point operations per clock tick per CU. We get 2 more zeros from there. 2 more come from the 110 CUs in each of those GCDs. 1 more zero comes from the fact that we have 8 GCDs per node. And then finally, Frontier itself is 9,408 nodes. There is the last of our zeros. Now, if you think about how long Frontier is going to be in operation, 1 day has about 10 to the 5th seconds, and in 3 years is about 10 to the 8th seconds. So if we add 8 onto 18, we get 10 to the 26 floating point operations. So we need to save the world in 10 to the 26 floating point operations, and we need people to write that code. Can anyone guess the mass of the Earth in kilograms? 10 to the what? The mass of the Earth in kilograms. Higher. Really good. 10 to the 25th. For every kilogram of mass of the Earth. And I don't know about you, but I think the Earth is really, really big. We can do 1, or I guess 10 floating point operations during the lifetime of Frontier. How about this? Number of atoms in the average human body. Remember Avogadro's number? Multiply that by a little bit more. Very close, 10 to the 28th. That number blew my mind. We're in the ballpark of doing a floating point operation for every atom in a human body. So I mentioned before scalable computing versus throughput computing. You cannot build an exascale machine in any reasonable amount of space or power or cost without a good network. If we had a crappy network, Frontier would have needed 5 or 10 times more nodes to just reach 1 exaflop. You've got to have a fast network. So Frontier is, as far as I can tell, the best in the world. It uses a thing called the Dragonfly topology, which was mentioned at this Exascale report in 2008. So this is not a new thing. What Dragonfly topology is, it doesn't look like a dragonfly, but it's in every hierarchical chunk of local network, there is an all-to-all communication possibility. So there's one Rosetta switch for some chunk of nodes for Frontier, and every one of those nodes can speak to every other node with 1 hop. Now, there's a lot of those chunks, and all those chunks are connected all-to-all as well. And there's one more level above that that's all-to-all to get to all 9,400 nodes. So ideally, there's no more than 3 hops between any nodes on this entire computer. And of course, the network is designed for low latency, high bandwidth. That's obviously we have to have that. What HPE Slingshot does that InfiniBand does not do is, and this is part of the Cray IP that's super important to making an exascale computer, is it has to perform active traffic management to avoid what's called worst case latency. So if your interconnect, for example, I'm not even sure of the numbers here, let's say some interconnect has 1 microsecond latency on average, and you have 100 nodes. Well, your worst case latency might be 2 microseconds. If you have 1,000 nodes, your worst case might be 5. And then if something weird goes wrong on one of the nodes, even at 10, especially at 10,000 nodes, even if your average latency is 1 microsecond, you could see 10, 20, 30 microseconds worst case latency. And because scalable computers are designed to solve huge problems concurrently, any slowdown means everyone has to slow down. So you cannot have those worst case latency issues. So Frontier's network, people knew this, designed a system to actively route traffic to get it to where it needs to be faster to avoid that worst case latency. Frontier is going to run different kinds of jobs across the network at the same time, and those processes have wildly different loads. They ask for network at a different time, so you need to have a network that responds to the immediate load and reduce that worst case latency. And this is another point that you'll hear me hammer home multiple times. When you work with 10,000 nodes, different problems crop up than if you only had a 1,000 node supercomputer. So this whole concept of working at exascale means caring about those very tiny, seemingly unimportant things, because any one of those could trip up a run. And just for fun, 81,000 cables, totaling 90 miles. There are people whose title is cabler, and they are very good at what they do. So the cooling is also kind of a novel thing for Frontier. In 2008, when we were looking at that last machine, those were all air-cooled. All supercomputers were air-cooled, or most supercomputers were air-cooled then. Water cooling has become more and more critical because you can pack more compute into a smaller space. Frontier takes this a little bit a step further, and it uses warm water cooling. And the difference here is that when you use a cold water cooled computer, obviously, when you run water through the CPUs and GPUs, it's going to heat up some amount of degrees, go back into a system that'll cool it back down and recycle it through. If you use a cold water cooled computer, you have to use something called the chiller, and those suck up a lot of power. Warm water cooling can use a different system to transfer heat to the air or to other water systems. And if you save that power, you can save power for the whole system. And you don't need to run, say, from like 50 degrees Fahrenheit to 70. You can run from 130 to, I don't really know how hot the water is, but it is definitely warm or hot water cooled, they call it. Part of the engineering of this machine isn't just the CPUs and GPUs. It isn't just the programming. It is all the other engineering things that go into making this work together tightly as one unified computer. And the weight of the coolant inside the computer has an effect. So you have to design your floor. You have to design your cabinets with the weight of the cooling fluid in mind. What is that? Okay. So in 2010, that report gave a number of predictions about what a exascale computer would be like, what the first one might be like in 2018. And we're going to kind of look through these and see where they guessed right and where technology took us in a different direction. So obviously the peak flops in 2010, the best supercomputer could do 2 petaflops, and Frontier made 1.1 in late May of this year before it submitted to the top 500. It was thought that an exascale computer could be made in 20 megawatts. Well, it turned out that was a really good guess. The HPL run that gave Frontier the top spot was average 21 megawatts. 29 is the peak power that we expect the machine to ever need to consume. But the overall power consumption of the space, it was built for 40 megawatts, because of course there's storage to go next to it, and there's other space for more machines. System side nodes, this is where the guess was kind of wrong. They were thinking 100,000 nodes. Turns out that we only needed 10,000 nodes. And this is kind of interesting because we are using much more powerful compute nodes than was expected in 2010. As you can see, the node performance, floating point operations per second for each node is 19 times bigger than what was expected. And a lot of that comes from this SIMD width. So 4 floating point operations per clock tick for each core was kind of expected back when they predicted. Frontier has these GPUs that do 64. So node concurrency, they were expecting 1,000 core CPUs. Well, the CPU is only 64 cores, but the development that this is really pointing to is that GPUs very soon after 2010 took over as the dominant compute apparatus for these large scale computers. You might not remember, in 2008 was the first NVIDIA GPU that had a relatively easy programming system. CUDA was released in 2008, and the 8800 GTX was released. And I remember, and Jim knows, and I'm sure Kaeli knows this, that kind of broke things open. We saw the immense power that these new GPUs could do, and it did that by much larger SIMD width and much higher concurrency. As far as memory goes, main system memory, pretty much nailed it. Really good guess. Node memory bandwidth, this is a lot higher simply because we have these larger nodes, these fatter nodes. And also because high bandwidth memory wasn't really in their view back in 2010. Interconnect bandwidth, pretty close, pretty accurate. Again, we have larger nodes, so we need a little bit more than was predicted. Storage, again, pretty good. I/O bandwidth, this is the bandwidth from the main computer to the main storage. This was less than expected. As it turns out, technology has been very good at giving us more floating point operations per area of silicon, but it has not been as good at giving us more bandwidth per wire. So this is the video that I spoke about before. This is the first time anyone outside of HPE or AMD or OCLF has seen this. This is a walkthrough of Frontier when it's actually doing work.
These are the rework stations where technicians perform repair actions for the machine. We're doing some power quality readings. Some other power quality readings. These are the electrical circuits that feed power. You can see through the top over to the machine. I swear I just heard it pause. That was weird. We've been looking at the harmonics. Several rows of these. We're running workload now. I can feel the heat coming off the cables, or coming off the hoses.
So that was a lot about the hardware. We're going to jump a little bit into the software and then go into some skills and the variety of jobs. Yeah.
So there's no fans? Huh?
Nope. Not that I know of. That's a moving part that's going to fail.
That's why one PM electrical engineer on
So we'll burn through some of the software information. This runs HPE Cray OS. This is based on Slackware Linux. There's a lot of system management software. A lot of engineers at HPE work on the OS, on fabric management software. There's a whole lib fabric that runs that layer of the communications. We have, of course, you have to customize your workload manager. Slurm is the one that is used on R. That's terrific. You're all ready. I even took the Slurm commands out of one of my slides thinking, oh, this is too technical. I want to put this in here. We're going to talk a little bit about communication because if you want your code to run fast, you want it to be on the 98% of each node that has the math power, and that's the GPUs. If you want to communicate, you don't want to have to send that back to the CPU to go through the network there. You want that to go through GPU-aware MPI. So Cray has its own libraries that manage that. It supports the HPE Cray is very happy about their software developing environment, but also you can compile with AMD ROCm and GNU compilers work as well. Lots of debugging tools. There are some specifically to help with the AMD GPUs, and then there are some larger ones that help you run GDB across a network of nodes. And then, of course, you're going to want to do profiling and performance analysis before you start running really big loads. Otherwise, you're wasting your time. So let's talk a little bit about how you want to program applications for the scale. First is don't do it. If someone already programmed it for you and you can use their tool, absolutely try to do that. If there's an existing library that almost does what you want it to do, consider contributing. Most of the tools that I work on as a performance engineer at HPE are open source. I just go to GitHub, clone it, talk to the programmers and say, all right, what's your performance issues? Or maybe I figure out what they are, and then we work together to make their code faster. If there isn't a tool that exists, consider using what are called performance portable frameworks for coding. And these are some of the popular ones are Cocos. Well, I don't want to say popular like everyone knows this. Popular in the field of people who need to program for these machines. Cocos is one of them. Raja, Intel's One API. Alpaca Kupla is a smaller one. And these are interesting. And another type is this directive based, which is the OpenMP offload. And you can do that with Fortran, whereas the other ones are exclusively C++. You have to add the MPI stuff yourself. Or if you wanted to, if you felt like it, if there isn't a code that works very well, or if those performance portable frameworks aren't going to work out for you, you can go straight to CUDA or HIP. If you haven't heard of HIP, HIP is AMD's version of CUDA. It looks a lot like it. It's intended to allow making programming of AMD GPUs easier. And if you're familiar with one, you should not have too much of a problem figuring out the other one. But again, MPI, learning how to do that scalably, that lands on you. Let's dive a little bit more into these performance portable frameworks that I mentioned. We've been programming for GPUs with nice ways like CUDA for 14 years. And in that time, we figured out, some things that are gonna stay constant. We've learned the hardware has kind of settled in this architecture. So people have decided to try to ease some of this load of moving data and trying to understand how you write a performance portable program that can run across a variety of compute hardware. That's what I just said. And it does that by abstracting the idea of execution spaces and memory spaces. Memory spaces obviously being on the CPU side or on the GPU side, or a shared memory space. Execution spaces being not just CPU or GPU, but other things that could be created in the future. Not sure what that's all about. And it does this again by managing arrays and data a little more closely than you'd expect. Usually you just pop open a standard vector, one for each MPI rank, and then do some work on that to trade information between nodes. But what you're going to do with one of these performance portable frameworks is create things called views. C++ is starting to consider arrays in this manner, and those can be moved around a little more cleanly. And one thing that ties all these together, One API, Raja, Cocos, is that the task code, which for CUDA would be called the device code. For OpenGL, it's the compute shader. These are programmed as C++ lambda, so it's right there in your C++ file. And then ideally, if the creators of the portable performance framework have done their job, you can run that same code on, like I said, a variety of hardware using multiple backends. So let's look at a really simple program in these three paradigms. So I'm trying to do a simple vector add on a GPU using C++ with OpenMP offload, using HIP, and using Cocos. So this looks pretty familiar, hopefully, to most of you. There's a big pragma OMP thing that says to distribute this workload across multiple teams and do it on the GPU. And OpenMP, the runtime, takes care of moving the data over, doing the compute, moving it back. HIP and CUDA are going to look a little more verbose. You need to be very specific about which elements you're working on, but by allowing yourself to use these languages, you have a lot more control over very specifically what happens, and you can squeeze the most power and performance out of these hardwares. And finally, Cocos might look a little weird. This is, again, like I said, we're not just going to make a standard vector. We're doing something called a view, and that view, we're giving it a space, this HIP managed space. This means like a shared, not shared memory, unified memory. So the runtime will determine when to move it over to the GPU, when to move it back. And that Cocos lambda is a placeholder for the bracket equals, the lambda capture by value for the C++ lambda. So some takeaways for what to think about when you are writing a code that's supposed to run on a very large number of machines, very large number of MPI rank. And one is you have to write for the GPU. There's no question about it. There will still be CPU supercomputers, but they will be few and far between. They will be powerful, but there are some codes that either are too hard to move to a GPU or don't have that level of parallelism. So think GPU. And by thinking GPU, you automatically are thinking of how to break your task up into millions of independent tasks, or billions, really, of independent tasks. You want to load data as infrequently as possible and as little as possible. So when you get it, do as much work as you can on it before throwing it away and pulling something else in. Like the memory hierarchy will do some of your work for you. It's great. But if you think about this from the beginning, you're going to write faster code. I guess I just said this. When you're setting out your data structures, this is as important as your algorithm. Use data structures or use your performance portable framework that lets you make data locality aware data structures. If you're debugging a code, you want to throw in some synchronization points. But when you run at scale, you want to have as few as possible. Every synchronization point is an opportunity for some node somewhere to be a little bit slower and slow your whole calculation down. And finally, for these big computers, if you're doing all your work and storing all your data on the GPU, you need to communicate your data from GPU to GPU. So however your machine lets you set up GPU aware MPI, use that. Think about that from the beginning. Yes?
So, you're going to have failures on these systems. So what are you doing for checkpoints?
That's obviously up to the application writer. Yes, there are failures. The goal is that you can run really large jobs for 12, 24 hours.
Hard to check.
There are systems. Okay, so some of the problems that you see at these massively large scales are like, say like the BIOS has a setting or a bug where like the clock speed for the CPU doesn't like it throttles too early or gets stuck at like a lower state. And that might happen only 1 in 1,000 nodes or 1 in 1,000 hours, but that's probably going to happen. So you obviously have to try to debug that or put in a better BIOS. Or what you can do is after every run, have it run a check to see whether that state is stuck and reboot the node or perform some fix after a job's done or after a job's failed. There are going to be job failures, of course. 2,400 nodes. We're even suggesting that because each node has 8 GPUs, you're going to run 8 MPI ranks per node. So you're typically going to run 76,000 MPI ranks if you're going to use the whole machine. And there are going to be failures on machines this big, but the goal is that's why we're building it. That's why we're shaking it down. We're trying to figure out where these things come from and eliminate them.
Do you use any standard framework for checkpoint?
There are a lot of libraries that do it, and it is kind of up to the application writer. There's no standard system for like dumping all the memory to a NVMe or anything. Okay, so now you've got it built, you got an account. What are you going to do? I mentioned this before. Make sure you turn on the flag that says use GPU or MPI. I can say srun commands here. Don't do -N8192 your first run. It's going to fail. Even the smartest people are going to screw up these things. If you don't start small, build up your knowledge base, and get ready to run at scale. You can do a lot, yeah. Yep. And again, so on each node, like I mentioned, think of it as 8 little mini computers, each one having 8 cores of the CPU and one 7400 processing element GPU. So that's a pretty good desktop machine. Think of each node as 8 of those machines. So run 8 MPI ranks on each one. I've written codes to use OpenMP one rank on each node. OpenMP doing 8 threads and is never as fast spooling up the GPUs as running the 8 MPI nodes, 8 MPI ranks. Little details like CPU 0 and 1. That's the first physical and the first hyper-threaded CPU. Those tend to run operating system jobs. So dash capital S2 is a good way to avoid using those first 2. And it turns out that on each NUMA node on these EPYC CPUs, that first CPU might slow down because it's doing operating system tasks. So I think it's dash S16 is going to block off those CPUs so you run on the next one that's not going to be slowed down by those tasks. So these are the kind of things that when you get to really large node counts, you have to pay attention to. You have to get this right, or else some node somewhere is going to send a signal that you didn't expect. It's going to slow down your whole run. And obviously binding, the SLARM option, GPU-bind equals closest, and GPUs per rank equals 1. This is the way to tell MPI to link the closest GPU, the fastest GPU, to that CPU core and make that one of your MPI ranks. And the way to make sure that happens is run xthi or hello job step, one of these simple commands with your whole SLARM statement, and see if all the ranks line up properly. I do this all the time. And finally, if you are writing data, and you probably will or should, there's a flag in the SBatch commands that turns on the NVMe. You got to do that for Frontier, and then write that data there. And then you can more slowly, or in the background, copy that data from the burst buffer drives, which is /mnt/bv. Copy that over to your home directory or some of the Scratch directory on the big 700 petabyte file system. You probably don't want to do that while you're computing, but you can definitely write checkpoints and write data files to the burst buffer. It's very, very fast. Not as fast as memory, but you need to write things out. So use the burst buffers. Yes?
So on Frontier, is there any smartness network GPUs? NVIDIA has this ability to sort of bump the wire type of operations where you can do reductions in the wire.
That's interesting. Not that I know on the Infinity Fabric on the AMD GPUs, but there are, I believe there's some research looking into in-network reductions on the MPI side of things, on the Rosetta switches. But that's not on node, that's intranode, internode.
Oh, it's internode.
Yes. Yes. No, that's very interesting. Yeah, thank you. That's a good question. Okay, we're gonna wrap it up with, not wrap it up. I'm gonna finish my part with skills you need to work at Exascale and going through some of the jobs that you need there. So in essence, this is not one person builds this thing. You need large teams, lots of skills, doing careful work and testing constantly to build something that will actually work at this scale. Simply because in a 60 million part machine, you got to get everything right. If one, like I said, there was a cooling tube that got crimped when a case was closed, and that node heated up, it shut down, and we go find that, see what's wrong with it. Things like that are easy because you look at it physically, the tech knew, oh, this is obviously the problem. But then there are weird things, like in your operating system, if you're running at scale, what are these little operating system noises that happen? You have to figure out what they are, shut them down if you can, and otherwise try to get consistent performance across all those nodes. And it takes a lot of skills to do this, a lot of different skills. So at the highest level, we build this machine for domain scientists. So you're going to get your PhD, you're going to get a postdoc, you're going to write a bunch of code in C++, and you're going to run it on these really big machines. You want to solve the big science problems of the day. This is where the domain scientists come in. So these are some skills you might need there. You're going to have to know your compiler inside and out. Super important. SPAC is, I don't think SPAC is used widely at Oak Ridge. It's still the, I'm sorry?
We developed a tutorial for AMD.
Oh, nice, that's terrific. Spec is used on many supercomputers, although the module system is what's on Frontier right now and is supported by OCLF. So again, learn Slurm. Looks like you're already ahead of the curve there. And lots of levels do this. It's not just professors that write this code. Professors have lots of people working for them.
Students.
They did. Absolutely. Lots of levels of people are needed for this. Don't think you've got to get a PhD to do this stuff. Benchmarking, this is close to what I do at HPE. These are people that help sell computers, of course, by taking specs from customers and projecting, can your code run the speed you want on the computers that we're selling. So lots of benchmarkers worked on Frontier. I work with those and doing the same kinds of work. So you have to really understand machine architecture, understand why a GPU is different, what MPI does, why the Slingshot MPI network is different. You have to really know your profilers. AMD just released OmniProf, which is a profiling tool that works on the AMD GPUs to go along with OmniTrace, which is a way of kind of looking at in a time series like what functions are happening, what the temperatures of your what the clock speeds of your CPUs and GPUs are. I'm already mentioned the PI. You still got to kind of know Fortran. There's a lot of Fortran codes that companies want benchmarked. They want to make sure that the machine they buy can run this, Fortran 77 piece of code. So you got to be familiar with that. And again, you have to know your compilers inside out. There might be a compile flag or a environment variable that you really need to have set to get everything to work on the machine that you're delivering. And again, you got to know Slurm. And like I said earlier, it kind of helps to know some Linux system internals. If you see little spikes of noise in your timings, you kind of need to know that it may or may not be the code, it may or may not be a runtime, it may be something on the machine itself. Obviously, you have lots of smart people around you to help you with these things, but it helps to have a familiarity. So AI machine learning engineers, you're typically going to be using existing libraries and tool chains. I think I list them in just a second. Kind of understand generally what the layers mean, what they do. TensorFlow, Keras, obviously, these are the two big ones. Or this is the big one, and the easy Python interface for it. Of course, you'll see a bunch of other machine learning libraries on these big machines. There's data movement, which is the critical part of why you'd even want to run machine learning on a large computer. You have a very large training set, for example. You got to move a lot of data around. Horavad and this Cray DL plugin, those are meant to assist that. NVIDIA has its own technology as well. And this is something that is kind of my personal beef. I really think people need to really understand what data is. Unfortunately, we have a lot of tools, phones and such, that try to hide this information from the user. You need to be smarter than that. You need to be more than just the user. You need to see what actually happens, what data gets moved, what it looks like, the formats for it, how to convert it, and how to use these very powerful tools to operate on it. So have an intuition for that. System administration, this is relatively straightforward, but things are different at scale. Again, rare failures are no longer rare. You have to automate a lot of what you do simply because you're looking at 9,400 nodes. Obviously, any large system will have thousands of users. You've got to manage those things. Know your compiler inside out. Know Slurm. This is pretty common. Absolutely. So it is not just programmers. I focus on that. This is the way my mind thinks. But obviously, to make a system like this, you need far more than that. I spoke with one of the people that coordinates a lot of this work, and I think he went on for about 70 minutes about all the different skills and all the different types of people that are required to build a machine like this, and a lot of more electrical engineers. HPE designs and makes these boards. HPE designs and makes the blades, the cases, the networking. You have to design their own chips to run the networking hardware. So there's a lot of electrical engineering and computer engineering work that goes into this. A lot of people who just need to move stuff, connect stuff. There's plumbers, there's electricians, even the drivers. You don't just put these computers on trucks to go from Wisconsin down to Tennessee. you got to make sure that they don't get shaken around too much. So there's temperature control that has to happen there. There's a lot of careful work that goes into this. Goes without saying, network engineers are hugely important. The slingshot, HPC slingshot technology allows us, like I said, to build an exascale computer with only 10,000 nodes and not needing a lot more to try to get that performance out, because we can solve these low latency problems. And it's not just that hardware, it's connecting it all, making sure it's connected, testing it, making sure nothing gets loose, and drivers and all that for it. And finally, you obviously have to design these cabinets. These are special cabinets. Each of them weighs 8,000 pounds. You have to not cut your finger on it. You have to not fall to the floor when you put water in the machine. You have to, try to design it to prevent crimping of tubes or wires. A lot of mechanical engineering goes into this. This is the important part here. And finally, where you'd go to get these kind of jobs? Well, obviously, Hewlett Packard Enterprise. My business card is in the middle table. You can scan the back for the barcode. We can talk to Danny, who will speak to you in just a few minutes about this. We have competitors too, have to say that. All full of very, very smart people. There's lots of work to do in this field. There's obviously hardware partners. HPE builds machines that have AMD CPUs and GPUs, that have NVIDIA stuff, Intel stuff, and those companies have their own similar jobs where they need people who can understand how jobs scale, how scalable computing works. So there's a lot of hardware and drivers, there's a lot of compiler development there as well. The person who gave this talk last term was an AMD employee named Nick Malaya. We work with him all the time. He's a hugely important person that helped make Exascale happen. You can work at the DOE labs. If you are subscribed to the High Performance Computing Jobs newsletter, there's always openings at Oak Ridge National Lab. There's typically openings at a lot of the other national labs. These are Department of Energy, United States government laboratories. A lot of smart people there, obviously, and these are the people that pay for and host these massive computers. Other DOE labs as well. You don't need to have an exascale computer to exercise your skills. There's lots of very large supercomputers at industry and in academia all over the world. So I'm going to pass it to Danny, who will talk a little bit about working at HPE. Danny, would you like to go over?
I am not going to take too much of your time. Probably there's 5 slides for me to go over. Before I jump in, do you want to look at the questions that you might have gotten from the chat, from the people that are viewed in?
Let's wait till the end.
Okay, I just saw that 4th thing. All right. So Amar.
After my section, I think we'll open up for questions. Thank you.
Great. As Mark says, my name is Daniela. I'm our TA lead for Hewlett Packard Enterprises. I've actually been here for a year, and I joined HP through an acquisition for Zerto, which is a data recovery and ransomware company. So HP's purpose is really advancing the way people live and work. I'm going to go over 4 of our beliefs. We believe in accelerating what's next. So our obsession starts with the customer. We always want to look beyond our competition and make sure that we commit and go. We also believe in making bold moves. We want people who are relentlessly curious. We embrace courage over comfort, and we're okay if you fail and learn from that and then improve. We believe in the power of yes, we can. Push to be better, demonstrate we before I, and exercise healthy impatience. We believe in, I already went over that, right? Yes. We believe in being a force for good, solve for humanity with humanity. We use technology to make the world better, and we are unconditionally inclusive. So here, I know most of you here are students, so our HP University program areas pretty much cover everything. So we have engineering, business and consulting, sales and marketing, global procurement, global security, global workforce, information technology, HR, which falls under me, and supply chain. So last year, we have hired over 1,000 graduates globally. We've had over 1,300 interns globally as well last year, and we hire in 40+ countries. So you can also move within HPE. Go ahead.
Co-ops?
So we do not do co-ops at the moment. And I know you guys are all co-ops. You can talk to me about internships from the Zerto perspective, because we actually have Northeastern co-ops at Zerto for our, I believe it's support engineering.
They're awesome.
They actually are. I think we've hired a few. I'll have this where to find us at the end so you can check it out. Look at our internship program. So you actually get assigned into projects to get a real life exposure to our leaders. You can connect with our other interns, and our key aspects of our internship programs are learning and professional development, social and networking events, and volunteer opportunities. We have some of the greatest benefits for staying healthy. So we obviously have the health plans, different wellness programs. You can actually win many different things just by like walking every day, which is great. Stress management programs. We have on-site fitness centers, gym memberships. We actually have an office in Andover. I don't know, Mark, if you go to it. And we also have an office in Seaport that I'm part of. And then we also have confidential counseling, self-help programs, and more. Money. We match 401k. We have Ernst & Young professional financial coach you can be part of. You can purchase our stock. We offer up to $9,000 for your student loans, health and savings accounts, and then different insurance options. Stuff you love. We have generous time off. We're actually talking about possibly having unlimited paid time off, 3 hours off each month for Wellness Fridays. But this is actually going to change, and you are going to have Fridays off instead of just 3 months off, once a month from spring to fall next year. So that's actually exciting. We have paid volunteer time, so you can actually do 40 hours of volunteer time, and that will be paid. You get exclusive discounts just for working at HPE. I use them all the time when I travel to Europe. We also have charitable contributions by matching by the HP Foundation. And then we have a great leave for new parents or adoption. It's 6 months at 100% paid, which is really great. Now what is our recruiting process? So we try to keep actually our recruiting process pretty short because we know there's a lot of competition out there. So your first step is to apply. Second is you will get a confirmation on your application. If you don't get a confirmation, I know you guys are probably going to start looking for jobs at some point. From the recruiter standpoint, if you're looking at jobs, not just with HP, but with other companies, and you see them and no one's responding to you, go on their LinkedIn, find a person that makes sense that you might have a connection with, and just send them an email. That's like, if someone applies, I might have 200 applications. I might not always get through them in time, but if someone messages me on LinkedIn, I will always respond to them and point them in the right direction. And then we have first interview, what you should expect. It's interviews are pretty much a two-way process. We want you to question us and interview us as much as we're interviewing you. And then, yeah, so we typically stay with 3 interviews. I know here it says 2 interviews, but you typically 3 interviews that we hold at HP. And then if all goes well, the stage 6 is employment. And this is where you can find us. Thank you, guys.
I'm just gonna leave this up. Just want to write it down. You have questions?
Yes.
All right, let's go.
So for the Exascale measurement that we're able to produce on the top 500, I know you talked about all the different options that you have available terms of different platforms for programming. And so we were getting it's for HPL. Was it in HIP and Rockham, or was it, I'm guessing it was using MPI? Was it using OpenMP as well?
I doubt it.
Okay. So just MPI.
I was not involved. I was hired the day after that announcement. Like that was my first day. But there's obviously a version of HPL.
I'm guessing the only way they can get that is with MPI. So that's pretty clear.
Absolutely. Yeah.
And
GPU or MPI, and I would have to assume it's a HIP Rockham version of HPL. Yeah.
And you know what libraries they were using or any?
No, sorry. Most of my work is focused on the domain science applications. So I'm looking at codes like particle and cell codes, the Cabana library. I'm looking at applied manufacturing stuff, like they want to stimulate how a laser melts, powdered metal and the flow that goes on in that and the microstructure that gets created from that. There are, of course, other codes that other people in my team are helping scientists out with. HAP, which is a astrophysics code. There's a gentleman in Timatics who's working on LAMPS. LAMPS is always one of the.
We did a lot of the LAMP supporting stuff.
LAMPS has turned out.
Yeah, I think we had. So we were doing
Oh, cool.
Yeah. And then we're currently working on a Julia port probably Oceanic, deep ocean model, and that hopefully will be running on the system. So that's great. And MPI running Julia, Pick and Rock.
Nice. Any other questions about hardware or software? I do my best to answer them. Yes, sir.
Software question. Earlier, you mentioned that you prefer to use MPI over OpenMP when GPU parallelism. Would that be because specifically the CPU connects that you have, or what was the reason for MPI?
Yeah, versus
MP.
For on-node parallelization, yeah, because there's eight GCDs. The obvious thing that I would think of is run one MPI job per node and then use OpenMP to get 8 A ranks. Well, what I found was that splitting up each of the GPUs, even if you put it in separate streams, was somehow serialized, which is kind of a strange behavior, and it might not be that way with later versions of Rockham. Also, when you're moving data between GCDs, if you're using OpenMP, it has to go back to the CPU and then bounce back up. So yeah, you're probably thinking that. But yes, when you're using MPI, that gets taken care of behind the scenes, thankfully, by the libfabric, and then other software that I unfortunately don't know too much about, but I trust that it works because I can see it working. Sure. I mean, my question is, where's the pizza?
It's coming. I think they're just going to
Cool.
make sure they can get in. I have a question. Why did HPC work with AMD?
When these things happen, so this is these Exascale computers, the first two, Frontier and El Capitan, are both on a project called Coral 2, CORAL-2, and that project was won by Cray 5 years ago, maybe. It was about $1 billion, and when Cray proposed that, it must have been in collaboration with AMD. They saw that the AMD CPUs and projected GPUs were enough to satisfy the Exascale requirement, and the Capitan computer that's going to come out, or that is being built right now, is going to use whatever the next, generation of MI whatevers are going to be. And the thing is, we had to ask DOE to start paying for this 5 years ago, not even having the first bit of hardware. But AMD proved to be a reliable partner, and the hardware is ready. Hardware's almost ready. There's a lot of things that have to happen for these big machines to occur. I mean, for example, Oak Ridge knew they had to create 40 megawatts more power for their computing branch. So they ran new power lines actually through like 15 miles or whatever of the woods in Tennessee to ensure that they had sufficient power for the cooling, the computer, the storage, and all that. That's what you have to plan multiple years ahead, and you've got to know this whole thing is going to come in well under 40 megawatts. And the HPL run, like I said, took 21 megawatts on average, 23 at the peak.
But I saw some kind of one or four. Four. Up to four. Let me see if I can see this question. Maybe you can see it.
Oh no, that's just yep.
What is the DOE's charter? Why do they do this?
Well, it says Department of Energy. It's interesting. So
is that spending energy or?
it is. It's the power essentially of energy. Energy is key to national power. And it began though as nuclear energy, nuclear power, and nuclear weapons. So there are several of the DOE national labs that are focused on what they call national stockpile. So they need to do physics simulations to try to avoid nuclear weapons failing, to try to avoid testing nuclear weapons physically. So they're Los Alamos National Lab, Lawrence Livermore National Lab, which is where El Capitan is going, and I know I'm missing one, Sandia. So big computers go there. They've got their own physics codes that are not on GitHub, surprise, that help them essentially maintain the nuclear stockpile. There's lots of very smart people working on that. They don't just do nuclear research, nuclear weapons research, they do a whole ton of other stuff. Oak Ridge National Lab, on the other hand, and Argonne, and there's one other one again that I'm embarrassed I forgot, are more of like more of open science labs. So professors from around the world, industry even can apply for time on computers at those labs. And Oak Ridge has been kind of like the leader on that side. Oak Ridge has had the #1 supercomputer probably more often than any other location in the world. And they focus on this open science stuff. So I'm on what's called the Frontier Center of Excellence. So I'm working with a team of people with similar skills that are helping these open science codes run efficiently and performant on the Frontier supercomputer. Whereas El Capitan, that's on the secret side. So there's another group of people that work on those codes. We, of course, share knowledge, and we have to understand what the architectures are going to look like. But that's kind of the division in the Department of Energy regarding the supercomputers. Yes, sir.
So, you guys talked about this a little bit, but, in recent years, we've moved to using GPUs for high performance computing because everything is so contingent on coding for operations and all that stuff. GPUs are great at that. Do you think can you envision a future in which that isn't the case anymore, where we're going to have bottleneck by coding for operations? And we might have to start looking at another computing architecture, or is that too forward thinking?
No, it's always smart to think about things in the long term for sure. I mean, like I said, we've had to plan this computer for 5 years. I'm not sure there will ever be a time where we don't need floating point performance, but I can see a time where we won't need it as much. Obviously, a lot of these new pieces of hardware are supporting, bfloat 16, even 8-bit floats or integer calculations, because those are the most prevalent types of calculations in machine learning. You might have read that Frontier itself, its hardware can support those lower precision operations. And I think Frontier achieved 6.88 exaflops on I think a bfloat 16 training test. But traditionally we use HPL, we use double precision computation to rate supercomputers, whatever that means. But obviously in the future, yes, there's going to be a lot more mixed precision simply because of the cost of moving a 64-bit double if you could get the same results out of a 16 or even two 16-bit bfloats. Your question was, yes, so there are, we're looking at quantum computing as well. I mean, HPE is clearly interested in this as well because we want to keep selling computers. Quantum computing can solve some problems, some interesting problems in very weird ways. And I'm only beginning to understand that. It's not going to take over some of the physics we're trying to do on supercomputers right now, but it will probably create new questions, which is what we want, right? Science doesn't necessarily want answers. We want to know what the next question is, and that drives where we go. So we're definitely looking at quantum computing, and there may easily be a time in 10 or 15 years where floating point isn't the number one goal for any machine, and that includes bfloat 16. But if you want fusion power, like there's a lot of stuff that's got to go on floating point performance wise to begin to understand and control those reactors, and that's kind of the save the world kind of like goal of supercomputing.
So your application work, have you started to use machine learning to guide computation?
I personally not,
You have.
but that is, it's not just not going away, it is coming fast. There are some really good results. For example, climate simulation. If you want to do a whole Earth climate simulator, Frontier is probably the first computer big enough to hold that at the resolution you need to resolve clouds. And it turns out that if you can't resolve clouds, you're going to get climate stuff wrong. So you can model clouds, but Frontier is at the scale where you can actually model clouds at like the probably kilometer level for a climate simulation. Now, for climate simulations, you're going to do ensemble simulations. You're going to do a lot of large simulations and kind of look at the averages. Well, if you're doing ensemble simulations, it's okay if you're a few % off, and machine learning can speed up a lot of the process and let you not stray more than a few % off. So absolutely, that's definitely going to happen. And it might already, I'm sure that's going to happen 2023 on Frontier. Yeah, so learn machine learning. I'm learning it. Don't let it learn you.
So I guess Frontier did not get on the green 500.
Frontier did, but not number one. Frontier was number 2 on the green 500.
What is?
The Frontier TPL, that test machine that I mentioned, the one rack, that was the run to get the green 500, because if you don't have to send things off the rack, you save a lot more power. So that one was, I think, 63 gigaflops per watt, whereas Frontier, the whole machine, was like 54. So numbers 1 and 2 for TPL, and then the regular Frontier. I mean, it's the advantage of new hardware. Lumi, for example, Lumi is the number 4 machine. HPE right now has number 1, number 3, number 1, number 4, number 7, number 10, something like that. And they're all the same hardware. They're all AMD EPYC CPUs and some large number of MI250Xs per node. Lumi is the one in Europe. It's their biggest supercomputer right now. I don't know if that's working or if it's still being stood up.
They're all AMD.
Those four biggie. Oh wait, no, one of them is A100s. Sorry, my bad. I think Perlmutter is number 7 or 8, and that's AMD EPYC CPUs, and then A100 GPUs.
Now Intel here.
Intel is building their Sapphire Rapids platform is going to be what is used on the Argonne exascale computer, which was going to be the first exascale computer, but they have had some delays with the Sapphire Rapids project, and Ponte Vecchio is the name of the GPU that's going to go into those. And I don't know the ratio of CPU to GPU for that. It's going to be similar enough to Frontier, similar node counts, similar number of GPUs and CPUs, but Intel's been having problems with their hardware, so that the room is ready. It's waiting for everything to come together. HPE is building the cabinets for that one and then networking. So again, the skills you'd learn programming for Frontier should mostly translate to that machine, which is called, tip of my tongue. It's Argonne, I think it's called Crossroads. Nope, it's not Crossroads. That's the one at Los Alamos. It's called something. And I mentioned one API, that's Intel's. Yeah. So if you can program Cocos or Raja, then one API should be relatively easy to learn. It uses this C++ Lambda syntax to do the compute kernels. And that's the whole goal of these performance portal frameworks. Yes, sir.
So in the video, I saw like roughly half a dozen workbenches. What's like the frequency of hardware failure?
I don't know, honestly, but there's always going to be at least one down. I mean, that's part of managing a supercomputer is you're going to pull blades, you're going to inspect them and put them back in. as you run large tests, you might say, oh, frontier 031401 is slow. Look into it. Someone looks into it. Maybe they pull it. Maybe they run some tests first and they pull it. Look at it. Almost always you have nodes down. The HPL run used not the whole machine. There's 9408 nodes. I think the HPL run used like 8800. Yeah.
Do you know what the most common cause of failure is?
I mean, it's feel like user error probably.
I was wondering about the cooling system. You guys see a lot of the cooling system, or not a lot.
Well, I mean, overheating's not a problem. It just throttles. But no, the cooling seems to be working very, very well. The only problems were those obvious ones where like one tube might have been pinched when a door was shut. But overall, the cooling seems to be working very well.
I can talk about GPUs. So to be part of this program, AMD had to do so much work to make their GPUs resilient to software, which are caused by particles in space or materials themselves, semiconductors. That basically would emit particles that don't fit.
I think all the HBM is error correcting memory.
Yeah.
That's very impressive.
Do you have another question? I'm sorry. All right. Well, again, thank you very much. Appreciate it. Please reach out to Danny or myself if you have any questions.
I mean, can we give you a little bit here?
Absolutely, yeah.
Yeah.
My card's right there. You scan it out for all the.
And that's my name, like, there's already very many of us like that. So, if I knew her.
Did I kill the Zoom already? So that. Oh, there it is. Okay. All right, everyone on Zoom, thanks for joining us.